Okay, so what are we actually trying to predict? In convection problems, engineers are ultimately interested in the wall shear stress because they want to calculate the drag and the pressure losses, for instance. They're interested in finding the heat transfer rate because maybe they want to size heaters, heat exchangers, coolers, need to apply insulation perhaps. And they're interested in finding the mass transfer rate because maybe they're sizing an evaporation unit, or they want to figure out how long it will take to dry perhaps a wet fluid, or if they're looking at absorption processes, for instance. Now, all of these depend on how rapidly velocity, temperature, or concentration changes near the wall. And so these rates are governed by wall gradients. When I say wall gradients, I'm using it synonymously as surface gradients. So these gradients, they cannot be guessed. They must be determined from physics. And so essentially in most flows, the fluid away from the surface is nearly uniform. So for instance, the velocity farther away from the plate will be at its free stream velocity, and the temperature farther away from the plate over here will be at the temperature of the bulk fluid, and the concentration farther away from this plate in the y direction will be the concentration of the species A in the binary mixture, which is essentially the free stream conditions. And so almost all resistances to transport occurs within, this thin region near the surface. And so boundary layer theory focuses on this region because it contains the strong gradients that we need to study, which essentially controls, the friction, the heat, and the mass transfer. Okay, so what is boundary layer theory? So let's start by saying boundary layer theory is a framework for describing the transport near the surfaces. It applies the fundamental conservation laws, such as the conservation of mass, the conservation of momentum, the conservation of energy, and the conservation of species. And these laws are applied specifically within this thin region, which is within this boundary thickness at the surface where these gradients are significant. And the purpose of it is not mathematical elegance, because if you look at the derivations for it, especially for the laminar flow, it could get complicated very quickly. But the whole point in going through this and showing it to you, and I'm not going to show you the derivation itself, but I'm going to walk you through the results, is to allow you to identify, so that you could identify the dominant physical mechanisms and relate the wall gradients to measurable quantities, and which will enable prediction of the friction, heat transfer, and mass transfer coefficients that you are trying to calculate. And so boundary layer theory tells us how the conservation law manifests near surfaces. Now, these are written as differential equations that describe how the velocity, the temperature, and the concentration vary in the flow. Now, these governing equations are difficult to solve in their full form because they're coupled. So the velocity affects the temperature and the concentration. They could be they're actually two-dimensional because they vary both in the case of the flat plate. They vary both in the x direction and in the y direction, and they are often non-linear. However, what we can do is we can simplify them, because the region of interest is just the thin boundary layer where the physics has a clear structure. So here are some of the simplifications that we do in order to be able to solve these conservation equations. So we first assume that the flow is steady, two-dimensional, incompressible, and has constant properties. Now, when I say incompressible, that doesn't mean that it's just liquids. I think as long as it's below 30% of 0.3 Mach, so 30% of its speed of sound, then it should be it can be considered incompressible or low speed. Now, we assume that the boundary layer thickness is small compared to with the surface length, and so changes normal to the wall occur over a much shorter distance than changes along the surface in the in the x direction. We can neglect streamwise diffusion, and streamwise diffusion is essentially diffusion in the x direction, which is diffusion along the advection, along the bulk motion. So diffusion along the surface is small compared with diffusion normal to the surface. We keep diffusion in the y direction and neglect essentially diffusion in the x direction. We can also assume that pressure across the boundary layer is nearly uniform. So pressure does not vary significantly in the direction normal to the wall, and that pressure within boundary layer is set by the outer stream flow. We can also assume that the velocity parallel to the wall is much larger than the velocity normal to the wall. So the x component of the velocity is a lot bigger than the y component. And so the cross-stream velocity exists, but it is relatively small and mainly supports boundary layer growth. And that this is only applicable for low speed flows, which is that viscous dissipation is negligible in the thermal energy balance. Remember how I said that the mechanical energy, let's say of a pump, gets converted to heat by viscous dissipation. And what I'm saying here is that in order to simplify the solution for the conservation equations that we're going to see the results of, we're going to make an assumption that the viscous dissipation heat is negligible, and so it won't be considered in the energy balance. So now that you know the simplifications, let's look at what the results look like for an example of laminar non-dimensional flow. The results here are non-dimensional, so what that means is that we've non-dimensionalized the results, and the reason we did that is because the point in doing or showing you this to begin with is because I want to highlight similarity parameters. And these similarities parameters are non-dimensional parameters that we get to see from the equations themselves once we start non-dimensionalizing them. So let's look at this table and try to understand what is going on. So first, before you look at the equations themselves and try to make meaning of them, let's first define what the variables are, because you could look at the velocity term, but it has an asterisk on it, and so it can be confusing. And so first we define L is a characteristic length for the surface of interest, and you get to see that in the Reynolds number over here, because if you look at any of these equations, you don't necessarily see L, but you see a parameter, which is the Reynolds number over here, and the Reynolds number is a function of the length. So the Reynolds number here is equal to the velocity, it's the upstream velocity, multiplied by the characteristic length of the surface, and in case of a flat plate, it will just be the length of the flat plate divided by the kinematic viscosity of the fluid. Capital V here, and that's the velocity upstream of the surface, and you don't see that in these conservation equations. You only see it when you look at the parameters in the equations themselves, so like the Reynolds number. Now let's look at the parameters that are with an asterisk. In order to non-dimensionalize a parameter, this is how we defined it. So an x with an asterisk is essentially the ratio of the distance x from the edge of the wall to the total length of the flat plate. Similarly, distance in the y direction, so the y asterisk is the ratio of any point in the y-axis as a ratio to the length, the characteristic length of the surface that we're interested in, and in terms of a flat plate, it will be the length of the flat plate. And the velocity with an asterisk is essentially the velocity at any point x divided by, or as a ratio to, the upstream velocity. So would be the free stream velocity. And you also have the velocity, which is the velocity in the y direction. So far when I've been referring to velocity, I've always mentioned the velocity in the direction of the bulk. But for the sake of completeness for the conservation equations, the velocity component in the y direction is v, the velocity component in the x direction is u. And so it also, for it to be non-dimensional, we divided that velocity by the same reference of the upstream velocity. And when we look at concentration and temperature, we define them as the concentration of the point at interest, which is x, minus the concentration at the surface over the difference between the bulk concentration and the surface concentration. And we did the same thing for the temperature, which is the non-dimensional temperature at any point x is the temperature at that point x minus the surface temperature over the bulk temperature minus the surface temperature. Okay, now we can look at these conservative equations and try to understand these terms. Okay, so let's try to look at the terms. So on the left-hand side, the first two terms, they're actually the advection terms. And the first advection term is the streamwise advection term. So it's the advection term going parallel to the plate. So it's in the direction of the bulk motion. And then the second term in the advection is the advection in the y direction, which is normal to the bulk of the flow. And then on the other hand side of the equation, for the momentum balance, we have a pressure gradient force term. But then the following term is the viscous diffusion term. Now, if you look at the thermal energy boundary conservation equation, we essentially have the same two terms on the left-hand side with respect to temperature, but essentially they are the advection terms, one in the streamwise and one in the y direction. And if you look at the concentration equations, you essentially have the same two components of advection that you need to consider for the stream, one in the streamwise direction, one in the y direction. And then if you look at the right-hand side of the equation for the thermal energy and the concentration, you're going to see that they are very similar. In fact, they are almost identical, except the only difference is the energy equation has Prandtl and the concentration equation has Schmidt. And Prandtl and Schmidt are both dimensionless numbers that I'm going to introduce to you. So Prandtl is a dimensionless number that is essentially the kinematic viscosity over the thermal diffusivity of the fluid. And I'll explain the relevance and the importance of that in the next slides. And Schmidt shows you the kinematic viscosity relative to the mass diffusivity of the fluid, and that also has its own importance that I will explain. So essentially with these boundary layer equations for the velocity, the thermal energy, and the concentration transfer, they all exhibit a strong mathematical similarity. So as you can see already just by looking at these equations, they're very similar. So in each case, you have the governing equation contains advection terms like we looked at that transport the fluid motion parallel to the surface, and this is the streamwise advection term. We also have the diffusion terms, which represent transport normal to the surface. So if you look at all of these diffusion terms, they are relative to the y-axis. And that is because if you remember, one of the assumptions we made is we said that the diffusion parallel to the surface or in the x direction is negligible compared to the y direction. You'd have to go back and look at the assumptions slide that we've discussed. Now, you could see that they're all similar because we've non-dimensionalized these equations and used appropriate scales for length, velocity, and temperatures, which is essentially the definitions here that I showed you. So non-dimensionalizing these conservative equations allowed us to be able to see the similarities in them, and it converts both the governing equation and their boundary conditions into the dimensionless forms and removes the dependence on absolute units, and it highlights the relative importance of physical effects. So let's see what the relative importance of these physical effects are. So after non-dimensionalizing these equations, which you can already see, the velocity, temperature, and concentration boundary layer equations differ only through a small number of dimensionless groups. So let's look at the Reynolds number, for instance. It appears in all three of the equations, and this characterizes the ratio of inertial to viscous forces, and thereby it governs the development and the thickness of the velocity boundary layer. The Prandtl number appears in the energy balance equation, and this number represents the ratio of momentum diffusivity to thermal diffusivity, and it indicates how rapidly heat diffuses relative to momentum. And the Schmidt number, this appears only in the concentration equation, and this represents the ratio of momentum diffusivity to mass diffusivity, and it indicates how rapidly mass diffuses relative to momentum. Now, for a given surface geometry and boundary condition, the dimensionless velocity equation depends only on Reynolds number. And so to summarize, for a given surface geometry and boundary conditions, and this is what you need to know, the dimensionless velocity equation depends only on Reynolds number, and the dimensionless energy equation depends only on Reynolds and Prandtl, and the concentration equation depends only on Reynolds and Schmidt. So now you might be wondering, how can I use these dimensionless numbers to solve for the heat and mass transfer coefficients? Well, let me now tie everything together and show you why the results of understanding the similarity parameters is important. And even though I showed you the results for results that are non-dimensionalized for laminar flow, these similarity parameters are also applicable to turbulent flow. And in fact, the learnings that we're doing with laminar flow are applicable to turbulent flow as well. So first, if we look at the non-dimensional momentum equation, we could see that it indicates that the non-dimensional velocity may depend on the following parameters. So if you look at this equation, you could see that the non-dimensional velocity can be a function of the non-dimensional x distance, the non-dimensional y distance, the Reynolds number, and the pressure drop, where the Reynolds number we saw depends on the upstream velocity multiplied by the characteristic length over the kinematic viscosity. And we know that the pressure drop depends on the surface geometry, and it's a function of the non-dimensional x value. And so if we substitute the non-dimensional parameters in shear stress equation, we get this. So what I essentially did over here is, this is the same shear stress equation that we are used to. So we know that the shear stress is equal to the viscosity multiplied by the gradient of the velocity at the wall, at the surface, evaluated at the surface. And so if I wanted to use the non-dimensional terms for velocity and for y, then all I'd do is I would substitute, I'd solve for u here, and I'd solve for y over here. And by doing that, I get to this expression for the shear stress. You can try it yourself. And then if you sub that shear stress expression, which is the non-dimensional shear stress expression, into the friction coefficient expression, which I showed you previously as this, then you will get an expression for the friction coefficient that has Reynolds number. And then we also know that for a prescribed surface, that the gradient of velocity at the surface is a function of non-dimensional x and Reynolds number. And so the friction coefficient then is just a function of the non-dimensional x and Reynolds number altogether. Now, leave the friction coefficient aside. Let's look at the Nusselt number. We know that the non-dimensional energy equation indicates that the non-dimensional temperature may depend on the following variables. If you look at the non-dimensional temperature, we know that it changes as in the x direction, it changes in the y direction. We know that there's a function, there's Reynolds number that it is dependent on, it may be dependent on, and Prandtl number as well, and a pressure drop that it may also be dependent on. So if we substitute the non-dimensional parameters in the heat transfer coefficient, we get, so this is the heat transfer coefficient equation that I've derived with you. And now if we non-dimensionalize that using the same definition, then what we will get essentially is that the heat transfer coefficient is equal to the thermal conductivity of the fluid over the characteristic length of the flat plate, or the characteristic length of whatever geometry you're using, multiplied by the non-dimensional gradient. So essentially the gradient of the non-dimensional temperature with respect to non-dimensional vertical distance evaluated at essentially the vertical distance of 0, so at the surface. Now, rearranging this expression will help define an important dimensionless parameter called the Nusselt number. So if you rearrange this equation to solve for the gradient of the non-dimensional temperature at the surface with respect to the vertical axis, then what you will get is the Nusselt number. And so the Nusselt number is essentially defined as and equal to the local convection heat transfer convection coefficient multiplied by the characteristic length divided by the thermal conductivity of the fluid. And that is equal to, from the equation, that must be equal to the gradient of the non-dimensional temperature with respect to the y-axis evaluated at the surface. Now for a prescribed geometry, then we know that Nusselt number is only a function of the non-dimensional distance and the Reynolds number and the Prandtl number. So this essentially implies that for a given geometry, the Nusselt number must be some universal function of the non-dimensional x, Reynolds number, and Prandtl number. And if this function is known, then it could be used to compute the value of Nusselt number for different fluids and for different values of upstream velocity and characteristic lengths. So from knowledge of Nusselt number, local convection coefficient may be found and the local heat flux may then be computed. And so if you integrate this over the surface, it will allow you to obtain the average heat transfer coefficient. So this correlation for the Nusselt number, which is the average Nusselt number, allows you to get the average heat transfer coefficient right away. So what you will find a lot of the times and what you will be expected to do is, for a given problem statement that you're trying to solve, you will get a correlation for the Nusselt number. And that correlation will be an average Nusselt number correlation. And you'll use that and you will solve for the average heat transfer coefficient once you know what the average Nusselt number is. And that will essentially be what you're going to be doing in a lot of the heat transfer problem statements. So in the future sections, you're going to see that you'll be given essentially Nusselt numbers for a lot of different geometries that you could use to calculate the average heat transfer coefficient. So this equation is very important for you to know. And this allows you to see that the Nusselt number that you will be given to calculate and to solve, it will be some equation that will be a function of the Reynolds number and the Prandtl number. So this is just a heads up. If you come across Nusselt numbers that you need to evaluate, more often than not, if not always the case, you'll see that it is a function of the Reynolds number and the Prandtl number. So this is a good sanity check. And we only got to know this because of the similarity parameters and because of the derivation that we didn't do, but we were able to take the results and observe them and make meaning of them and understand what to look out for when we solve these problems. So for the Sherwood number, now the Sherwood number essentially is derived in the same way. So we look at the non-dimensional concentration equation that indicates that the non-dimensional concentration may depend on the following parameters, which is the x-axis, the y-axis, the Reynolds number, and instead of the Prandtl number, we have the Schmidt's number and the pressure drop. And if we substitute the non-dimensional parameters in the mass transfer coefficient, this is the mass transfer coefficient we derived together. And if we non-dimensionalize that by substituting for this non-dimensional equation that we've also used so as to be consistent, then we get the mass transfer coefficient, convective mass transfer coefficient, to be equal to the diffusion coefficient divided by the characteristic length, all of that multiplied by the gradient of the non-dimensional concentration with respect to the vertical axis evaluated at the surface. Again, we're going to do the same thing. So if we rearrange this expression, this defines an important dimensionless parameter, which is the Sherwood number. And the Sherwood number is essentially the mass transfer coefficient multiplied by the characteristic length divided by the diffusion coefficient. And that would essentially equal to the non-dimensional concentration gradient with respect to the vertical axis evaluated at the surface. And so for a prescribed geometry, just like the Nusselt number or the heat transfer, the Sherwood number is a function of x, the Reynolds number, Schmidt's number. And similarly, you're going to find relationships for the Sherwood number, the average Sherwood number. And when you use a relationship for an average Sherwood number, that would give you the average mass transfer coefficient. And just a heads up, more often than not, if not all the time, you're going to find that the Sherwood number that you find correlation online to use will be a function of the Reynolds number and the Schmidt's number. Okay, so these relationships essentially show why the Nusselt number is required to calculate the heat transfer coefficient, because you could see that the relationship between the heat transfer coefficient and the Nusselt number. So without knowing the Nusselt number, you might not be able to calculate the heat transfer coefficient. And in engineering literature and the scientific community, they'll give you the average Nusselt number correlations, equations for different geometries, and you'll need to plug in your Reynolds number and your Prandtl number in some kind of analytical equation or experimental equation that will give you a Nusselt number, an average Nusselt number, that then afterwards you're going to have to solve for the average heat transfer coefficient. I'm just giving you a heads up of what you should expect. And these relationships show you why the Sherwood number as well is required to calculate the mass transfer coefficient, because you could see the relationship. These dimensionless numbers arise naturally because heat and mass transfer coefficients are directly related to dimensionless wall gradients of temperature and concentration. Because don't you see essentially that the Nusselt number over here is essentially equal to or is defined as the non-dimensional temperature gradient at the surface with respect to the vertical axis. And in terms of concentration, the Sherwood number is naturally or defined as the concentration gradient the non-dimensional concentration gradient with respect to the vertical axis evaluated at the surface. So essentially, these dimensionless numbers allow you to calculate these mass and heat transfer coefficients because of how they relate to the gradients. In the next sections or chapters, we're going to use now what we've learned now. So we're going to use the Nusselt number correlations for different surface geometries expressed as a function of Reynolds and Prandtl, as I mentioned. And for Sherwood, we're going to look at the Sherwood number correlations for different surface geometries expressed as a function of Reynolds and Schmidt numbers. So when we look and see these non-dimensionless equations, we shouldn't be surprised when we see they're related to Reynolds or Prandtl or Reynolds and Schmidt's, because based off this discussion, we are aware that that should be the case. And to calculate the average heat transfer coefficient, we're going to have to evaluate the Nusselt number first. See you in the next video.